All right, in this problem, make sure it's focused in. In this problem, we are going to look at this system in which I have a rocket, a toy rocket, which I have attached rigidly to a bar of length L. I'm given that this bar has a mass. I'm given that the rocket has a mass. And I'm going to fire the rocket. It's going to put out a force that I'm told. I've labeled that F sub r. And it's going to rotate in a circle, which is this dotted line. It's the bar is rigidly attached here, and this thing is going to rotate in a circle. So I've written my knowns here. I've got m sub t, which is I'm calling the mass of the toy. That's the mass of the rocket here. And then m sub r is the mass of the bar. I've got that the length of the bar is 0.2 meters. Theta, notice the rocket makes an angle of theta with this radial line. I'm going to assume that this is rigidly attached, which means its theta is not going to change as this moves around. It always makes an angle of theta with the radial line here. And the force of the rocket is 75 newtons. So the first thing I've done is not necessary, but I find it to be useful. I have two different masses, and I've got subscripts on my masses. I don't like subscripts if I can help it. So I'm going to express these masses in terms of each other. I've got the mass of the rod is 10 kilograms, mass of the toy is 12 kilograms. So I just express this 10 kilograms as m, and this 12 kilograms as 1.2 m. Again, you don't have to do that. I find it to be helpful because later we're going to usually see that you can cancel m's from terms, and you're just left with the ratio here. So that's just a little trick I do. Again, not necessary. I've already started the problem. Sorry, I had to start over the video because I made a mistake, but it's okay. So the first thing I'm asked to do is treating the rocket as a point mass. Determine the moment of inertia of the rod-rocket system. So this thing is going to rotate, and this bar has a mass. That means I can't just treat it like a string and ignore its moment of inertia. I've got to take into account the fact that I have a mass that's rotating about a point. So I've got a rocket that I'm told to treat as a point mass, and then I've got a bar. Well, I've got a compound object. So the moment of inertia of a compound object is just the simple summation of the moments of inertia of the individual objects. And so that's what I've written here. I total is I of the toy plus I of the bar. All right, so to find this out, I'm told to treat the toy as a point mass. If I go look up the moment of inertia of a point mass, I find that it's mr squared, where r is the distance between the thing, the point mass, and the point of rotation. So I can treat that thusly. I need the mass of the rocket. That's the mass of the toy. That's 1.2 m, 1.2 m. That's the mass times the distance squared. Well, the distance between this point mass and the center of the circle is just little l. So I will have little l squared. Of course, I have a value for little l that I can put in later if I need to. So that's the moment of inertia of the point mass rocket. Now, moment of inertia of the bar. Well, if I go look on a chart of moments of inertia, I find that the moment of inertia of a rod about its end, I'm rotating about the end of the rod, I find that's 1/3 ml squared. So plus 1/3. Now, what is the mass of this bar? Well, the mass of the rod is what I've called just m. So I get 1/3 from the moment of inertia definition, m. And the length of that rod is also little l squared. All right. So what I have here, if I just put all that together, I've got ml squared times 1.2 plus 1/3. Well, let's go ahead and consider 1/3 to be 0.33, which means I can get away with saying 1.2 plus 0.33 is 1.53. Okay, so I do have a number. If you're in my class, you know that I like symbolic solutions first. So this is a number, but it's not one of my givens. This is just a ratio of masses. It enables me to write this simply. Okay, so that's the moment of inertia of my rod and toy system. Now, part B, determine the total torque applied to the system. And notice I say, recall that we're looking at this from above, and what that means is that gravity is acting downwards, and it's not going to apply a torque that I have to worry about this axis, I should say. The torque gravity applies is about a different axis. We're not going to worry about that in this class. All we're going to worry about is the torque produced by this rocket, the force of the rocket. So to figure that out, I need to first draw a free body diagram of that thing. So I've got the rod, this is part B. I've got the rod, and I've got the rocket. I'm going to treat the rocket as a point mass. And I've got this length L, and I've got that the force of the rocket is here, theta. Well, to determine the torques, first question, it says, if I say find the torque, you go, about which point? That is critical. Any point in the universe works, but there are some that are more clever than others. This is actually rotating about this point, so I think summing the torques about this point is the best choice. So my next step is to take this force, I should label it F sub r, and break it up into perpendicular and parallel components. The perpendicular to what? Perpendicular to the r vector, which connects my point of summation, which is in this case a point of rotation, to the force itself. That's right along here. So let me break this up into parallel components. I've got that, and I've got that. This, I should say parallel and perpendicular components. So this is my parallel component. How much torque does this component provide about this point? The answer is none. Remember, you can't open a door by pushing towards the hinges. You can't open it by pulling away from the hinges as well. So the parallel component here provides no torque about this point, only the perpendicular component. If I look at the right triangle I've got here, this component is FR sine of theta, as I've drawn it here. So if I want to know the torque, the only force I have acting that I'm worried about, again, I'm not worried about gravity in this case, I've got F sub r, and then sine of theta. That's the component of the force that's causing the torque. And I've got the length L, and now I need to worry about the direction. If this force were to act by itself, then this would cause a counterclockwise rotation, so I'm going to call that positive. Okay. I should point out that my free body diagram is not actually complete. I've also got a pin here. I've got some sort of support force from the pin. But if I'm summing the torques about this point, remember this is the clever choice because this force is applied at that point. And any force applied, any force, I should say, no force provides a torque about its own point of application. So the free body diagram to be complete should include this. I've probably drawn it in the wrong direction, but remember, this is usually the one I have to guess on, and whether or not I'm right or wrong comes out in the wash as I run through the mathematics. It looks like I've guessed wrong as far as the up-down direction. But it doesn't really matter because it's not appearing in my torque equation. If I need to calculate this later, I can do it by other means. For torque, this force provides no torque about that point. So all I have is this expression here. That's part B. All right, part C, determine the angular acceleration experienced by the rocket. Well, to do that, I need Newton's second law in rotational form. The sum of the torques is equal to I alpha. Fortunately, I've already found pretty much everything I need here. The sum of the torques, well, the only force providing a torque about this point is F sub r. I've already calculated the torque due to F sub r. So that's all I have on the left-hand side. I've got F sub r. I'll write the L here because I don't like writing things after the angles. But that's the torque, and that's equal to I total alpha. Therefore, alpha is equal to the left-hand side divided by I total. That's F sub r L sine of theta divided by I total, which I have 1.53 ml squared. Okay, I can get rid of an L. That's going to leave me with F, not R, F sub r sine theta over 1.53 ml. and that's going to be the angular acceleration experienced by this system. Okay, now part D says determine the angular displacement through which the system has moved starting from rest after 3.5 seconds. So I've been doing this in a true rotational paradigm, but if I want to know the angular displacement, probably my best bet is to look at kinematics. I've got an acceleration here, which notice is constant. None of this stuff changes. So I've got an angular acceleration, which is constant. I need an angular displacement, and I know that it starts from rest. All that is waving a red flag at me, yelling kinematics, angular kinematics. So if I need a displacement, I'm probably going to pick this expression, delta theta is equal to omega, the angular velocity initial, times time, plus 1/2 alpha, angular acceleration, t squared. Well, I start from rest, so the initial angular velocity, omega initial, is 0. And it looks like I have delta theta is equal to 1/2 my angular acceleration, which is all this, times t squared. I'm given t. T is 3.5 seconds. And this running these numbers will get me the angular displacement after that amount of time. So I've given you the symbolic solutions here. I'm going to trust that if you really want the numbers, you can put them into a calculator. I'm happy with the symbolic solutions here. I basically gave you numbers because I wanted you to see this little trick. We're going to see it in the other two problems as well. But this is what I have for this problem. If you have any questions about that, we can address that next week or send me an email.